Good afternoon. Oh, excellent. I can hear myself. Hi. Very happy to see all of you here. My name is Oleg Šelajev. I come from Estonia. It's a small Eastern European country. I work as a developer advocate for Oracle Labs. I work on the GraalVM team. And today we're going to talk about GraalVM, which is a very exciting project. And hopefully we're going to learn many interesting things about it and how you can maybe leverage it, start experimenting with it, and why it is very popular. So before we start, we have 50 minutes. We're going to use all of them until they kick me off stage. And you will have a chance to ask questions. If you don't get a chance to ask questions here, I will be at the booth in the expo area, where you can find me online. I'm almost universally go by @Šelajev. Right, so you can tweet at me, and I will be able to answer your questions or forward you to people who know more than me. Recently I turned 30, and I feel like I'm old and wise, and I can give advice, not just about software development, but about life in general. So if you want, you can ping me. Right. GraalVM. Before we start, do not make any forward-going business decisions based on the contents of this presentation. That is very important. Thank you. And with that mandatory thing out of the view, let's talk about technology. How many of you, who has heard of GraalVM? Right. Excellent. Almost everyone. So makes me very happy. As a developer advocate, one of my responsibilities is to make sure people are aware of our projects. So who here feels like they can explain what GraalVM is? That's the second step. Besides recognizing the name, it's also very important that people understand what it does. So hopefully this session will be exactly for you because, well, you're here, you're interested, and I'm here to explain the details. So in one sentence, what GraalVM is a high-performance polyglot embeddable virtual machine capable of running programs in different languages. High performance, embeddable, polyglot, different languages, right? And it can run them in different setups as well. So if you are gonna, if anyone will ask you what GraalVM is, this is one line that you want to remember. If anyone will ask you, why would you care about GraalVM, right? There are plenty of virtual machines. Every language programs in any language can be executed already, right? It doesn't seem like a groundbreaking. But there are a number of really great advantages to what GraalVM currently presents you with and why you can use it. So it's a high-performance virtual machine, so it can run programs faster than other runtimes, right? So you can just win on performance, and this is one way. So it's a Java virtual machine, right? It can run Java programs. Anything that compiles to Java bytecode can be run on it. And if you want a faster runtime for your Java or Scala applications, you are welcome to try. And we'll show a demo of that. There is a mode in GraalVM that it can process your programs and then convert them to a native executable. And in that mode, it can offer you an instant startup and really small runtime memory overhead for your programs. So if you're running something in the cloud where your startup costs are important and where your runtime memory overhead is important, then you might be interested in looking into this. It's a polyglot VM, so if you employ or you wield, so to speak, different languages, you might be interested in building a system out of components written in different languages. It could be interop between Java and JavaScript, or it could be a node application that leverages some Java libraries. Depending on what languages you use, it might offer you the polyglot capabilities. And you can mix them, you can interop with them, and most importantly, you can embed the GraalVM technology into your Java or native platforms. So if you have like a large application, maybe a database, you might want to enrich that with capability of running JavaScript. And it doesn't have to be a database. It could be like a streaming platform or like any large Java application. If you want to enrich that with other languages, GraalVM might be a very interesting choice for you. So if you will remember one slide, one thing out of this session, I want it to be my Twitter handle, of course, but probably it's better if this is this slide, right? This is one picture that explains the capabilities of GraalVM and what it is. It's a runtime, so it sits between the underlying platforms and the programs written in languages. Currently, we support JVM languages, JavaScript, Ruby, R, Python, and native languages. Everything that goes through the LLVM toolchain, right, through the LLVM compiler, can be run on GraalVM. It works by translating the program, it starts running your programs, and then it compiles them at runtime, just-in-time way, into a very efficient machine code. So there is special technology, and I'm going to show it a little bit today about how we can achieve really good performance even on those dynamic languages that are known not to be the fastest, right? Nobody usually claims that R is a very fast language. But we want our software to be fast because, well, life is too short to wait for software to complete things. And we can automatically transform interpreters for those languages into efficient compilers. And then the platform integrates in different actual runtime options. So we can run your programs in the context of the JVM, like on the normal JVM. Usually that would be an OpenJDK build. We can run it in a node application. And that would be the proper node application with the event loop, with the signal handlers that node registers, and you can use all those languages there. Or it can be embedded into an application, or some applications can be compiled to the native executable for the fast startup, right? So there are different languages, and there are different ways how we can execute those languages. So now a reasonable person would understand that those different modes can come with different terms and conditions and limitations and what it can do and how well it can do things. So now, if somebody will tell you something about GraalVM, what you would do, you would ask which one of them do they keep in mind, right? Do they use GraalVM to run in the context of the JVM or a standalone native image or anything like that, right? So, but we'll cover this, right? This slide. Everyone is on board with this slide. Let's talk about technical details a little bit more. You can obtain GraalVM. You can get the distribution. You can download it from the internet. It comes packaged as a archive. I don't think it's a zip archive, but you can unzip it, right? And it will look very similar to your normal JDK distribution that you get to get. So you can see there are normal Java commands. So there is Java, Java-C, Java doc, JHat, and so on. But there are also commands normal in other platforms. For example, we have Node and NPM because we can run Node applications as well. And there is also other languages like GraalPython to execute Python scripts, Ruby, are all there. So it's a single distribution that can be filled with different capabilities for different languages, right? So if you would like to use GraalVM as say a Java runtime, all you need to do is to download the archive, unzip it, change the path to the Java executable, right? Put this directory on your path, and then when you type Java, this one will start working, right? And that could give you a performance boost. How amazing is that? If you did any performance work in the past, you know this is the easiest way to get performance boost. It never comes as easy as this. So you should be interested. So let's talk about how it works. When we run, say, Java command from that, it starts normal JVM. So the underlying platform will be JVM. And in our builds, this is Java Hotspot VM. And then we enhance that with the GraalVM compiler. It comes from the GraalVM project, and it integrates with the JVM using JVM CI. JVM CI is, of course, the Java Virtual Machine Compiler interface. And this is the normal interface added to OpenJDK, I think in JEP 243. It was added to Java 9. And this is the normal way how you would write and supplement a JVM with a third-party compiler. the just-in-time compiler, right? The thing that takes the bytecode and produces machine code. If you want to write a compiler, you will implement that interface. Now, we backported that for our builds to... I'm sorry, like, is the sound okay? Because it feels weird a little bit. Okay. We backported the JVM CI interface to Java 8 builds, so we provide binaries based on Java 8 currently, right? Who runs Java 8 in production? Excellent, everyone. Who runs Java 9 Plus? Very good, 20%. That's excellent. We're gonna talk about you a little bit as well, but most people here run Java 8, so you can just download those and change the path and see where it leads you, right? So with those two things, we can run Java programs as they would normally run on the JVM. So JVM will start, JVM will load the classes, it will start executing your program dynamically as usually. It will find the profile and it will be like, oh, this method is getting called a lot, so I should probably compile that to an efficient machine code. And it will pass it to the compiler, and the compiler will take the bytecode, take the profile that, OK, this method only gets small integers or only gets strings that are shorter than 3 characters, and give back an efficient machine code. That is what a JIT compiler does. So Ground compiler can be used this way, and through that machinery, we can run Java programs easy, right? Because anything that compiles to Java bytecode will just run on top of those things. The other languages are a different story. So normally, if you want to implement a support for a programming language to run on top of the JVM or any other platform, you need to translate the concepts from that language. What does it mean to have like say a Kotlin coroutine or like a Ruby block? And how does that concept translate to the underlying platform vocabulary? How to translate from that to Java bytecode? And this is a hard and very complex challenge because languages evolve. Languages, sometimes they have the similar model to Java languages and they nicely translate to bytecode. Sometimes they're not. For example, JavaScript is much more dynamic than Java. So some concept will be much harder translatable into Java bytecode. So to overcome that challenge, we took the different route. And when I say we, the Oracle Labs team, which I joined very recently. So it was before my time. It's a different we. So we implemented a framework for creating managed languages called the Truffle Framework. What it gives you an API to implement a language interpreter. So you need to fix the semantics of the language by writing a program in Java that knows how to interpret programs in other languages. So you don't translate it manually into the low-level concepts, but you just provide a high-level interpreter to evaluate programs. And normally that would be extremely slow, because imagine you will have to parse and build the program graph, and then you suddenly start evaluating every operation. So to evaluate an expression like a plus b, you need 3 virtual calls. You need to evaluate a, you need to evaluate b, you need to evaluate plus. 3 virtual calls for 1 addition, that is not the performance that anyone would be happy with, right? So with Truffle Framework, that interpreter can be at runtime compiled very efficiently. First, at the interpreter level, and then it is passed to the Graal compiler, which sits below there, and it gets compiled once again at a lower level. So there are 2 high-level optimizations happening, and that's how we get very decent performance out of the dynamic languages. So we implemented on top of the Truffle Framework, on top of the GraalVM, we implemented Ruby, R, JavaScript, and Python. So to get node integration, we took the actual node, took the V8, the virtual machine for running JavaScript that's normally in Node. We took it out, and we put our JavaScript engine into Node. Right? That's how we can run Node applications. And the same way, we implemented support for LLVM bitcode. Right? So anything that compiles natively can probably go through LLVM. LLVM bitcode is kind of very similar to the Java bytecode. It's an intermediate representation of the program. And we can interpret that, and we can run that. The benefit of this approach is that when dynamic languages use native extensions. When somebody writes a Python module, and they're like, oh, this is not fast enough. I need to replace this critical section with some native code. They suddenly rewrite that in say, C or C++. So we want to run the ecosystem of the modules in all those languages as it is, right? So we would like to run Python modules, including the Python extensions. So we needed a way to run native code on top of our execution stack. So that's where the LLVM comes in, right? And all those things, they look very similar. Currently, Java and JVM bytecode a little bit less similar, but all those languages look absolutely the same to the underlying platform, which means that we can integrate the tooling, like debuggers and profilers and everything, with the Graal framework, right? And those languages will get support for that for free. So this is how it works. How you can see it and how you can touch it. It's an open source project. It's available on GitHub. It's written in Java, which is very good because most Java developers, I assume, who writes Java every week at least. Excellent. Who writes other JVM languages? Scala people. Very nice. We show really good results for Scala programs, so there is no excuse for you not to try it now. You can look at it. It's written in Java, so you can load it into your IDE. You can go through, click through classes and see what it actually does, and you can understand what it does. It still takes a little bit of effort to become an actual compiler engineer, but allegedly it's much easier than go and enhance native compilers. So an open source project, you can build it yourself if you want. If you don't want to build it, you can download our builds, right? We provide binaries for Linux, Mac OS, and allegedly very soon for like a preview of Windows builds. And you can get them. There is a community edition, which is the open source components built by us. And there is also free to use with the respective open source licenses. And there is an enterprise edition, which is the Oracle product, which you potentially can purchase. And it comes with a more powerful compiler with more optimization phases, and it gives you even better performance. And some other enterprise-looking features. So you can try that. Currently, it's available from the Oracle Technology Network website. You can download that. You can evaluate that. You can see how it works. But if you really want to use the open source bits first and then opt into additional performance later if you want, then they're functionally the same. So they will be able to run the same programs, both editions, right? So that's how we can get it. And just earlier today, Eric Seller announced at a session here that Oracle GraalVM Enterprise is an actual Oracle product. And this is very exciting for us and the team, and hopefully for the whole community, because it's a very large undertaking, and being able to have a sane monetization way for the project is very important. I mean, not monetization, but quotes were for sane, right? You can opt into that if you want. Right. So let's not talk about it anymore. Let's see how it works. So I have my sample project here, and I will run a sample benchmark. It's a very simple benchmark written with JMH. It's not like super reflective of the code you write daily, unless you stream an array of 10 integers and pass it through 3 map functions. If you don't write hello worlds for a living, you write a little bit more complex code. But this is very representative of the modern Java workloads, right? It uses Stream API. It passes methods, references to map functions, right? It is something that you could easily find in the code base, like maybe in a small sample. So we're going to run this benchmark. It is written using JMH, which means that it makes it a little bit harder to do a very wrong thing running the benchmark. So I'm going to use Java executable from my GraalVM home directory, and I will pass it this interesting command line option. I will disable the use of JVM CI compiler, right? So when I said that the JVM CI compiler, the GraalVM compiler integrates with JVM, there is a command line option to turn it on and off, of course. So first, to run this benchmark, I wanted to show you that there is no tricks, right? I will run it without the GraalVM compiler involved. This would use the normal setup. It will use JDK 180.212, and it will run with the normal C2 compiler as the top tier compiler, right? This is normal Java. What OpenJDK will show the same results, right? Because there is no GraalVM compiler involved. It's going to run for 40 seconds, but I just want to show you that there are no tricks. I feel that this is very important. Right, so we can see that it warms up a little bit, and then it shows 3 iterations. We're going to run 3 of those, and it takes 180 nanoseconds to run 1 iteration of this test method, right? We see the results. Not the most rigorous benchmarking setup here, but maybe it will be indicative of something, right? Now I will run with GraalVM compiler enabled, so I will not disable that. So now the Graal compiler will be able to do what it does best, right? And I will not show you the results. We were going to look at the code for half a minute, not to spoil the surprise. So so we are comparing 2 platforms here, right? Who thinks the GraalVM will be faster than the C2 compiler? Who thinks it will be faster? OK. Who thinks it will be slower or the same? JVM is a very state-of-the-art virtual machine. It's very hard to be faster than normal JVM. That's why we write Java daily, right? But you think it will be faster. Very true, very smart. I wouldn't show you the benchmark where we are slower. But the question is, how much faster? Right? Who thinks it will be 10% faster? 10% is a lot. 10% can get you a low latency garbage collection for free. Who thinks it will be 20% faster? That's quite a bit. 50% faster? That's ridiculous. Twice as fast. I want to see who is the most optimistic person here. Excellent. Yeah, let's show. I think half a minute has passed. So we can see that after this short run, 1 iteration of this test method runs in 10, well, maybe 20 nanoseconds per operation. Before, it was 180. 10. That's 18 times faster. That is ridiculous. The ridiculousness of this comes from the fact that Graal compiler is sophisticated enough to optimize this benchmark really, really well. So this result is not indicative of the future performance, right? You shouldn't expect that you will switch your Java executable and suddenly your programs are 18 times faster. But there are no On the other hand, there are no specific tricks in the GraalVM compiler to say that when you see the benchmark like this, please just do it very, very fast, right? It's just the result of the generic optimizations, so any code can be sped up considerably, right? The exact performance boost depends on your workload, depends on your code, depends on your frameworks, and so on, but it could be very considerable, right? You saw that even for 10% faster, not everyone believed that. I mean, maybe some people just didn't want to raise their hands, but it's a challenge, right? So being faster than normally is a very great deal. If you run your deployments in the cloud and you actually pay for the cloud, you pay for your compute power, being faster means that you're saving money. So if you look at how much faster you can be considerably faster. So we run a number of benchmarks. We run tons of benchmarks like every day. But this was interesting, and we blogged about that on the team blog. We run a number of benchmarks using Stream APIs, and we saw really good improvements on that. So I think typically it was like 2 times faster or maybe higher compared to Hotspot. We run Scala, and we run tons of benchmarks. For Scala, it's even better. I think the Enterprise Edition gives you something like 30% boost or like 40% boost. The Community Edition gives something like 10, 12%, which is excellent that you can just swap your executable and get that. In general, we run a lot of benchmarks. We recently, there was a paper about the Renaissance suite, like an aggregate of the benchmark for modern Java workloads. So this one gathers benchmarks about akka, about Neo4j, about reactive extensions. So the code that actually is representative of the applications we're writing right now, right? So maybe some other benchmarks which are a little bit older, right? Maybe they just test different parts of the compiler, right? Different optimizations or something. So maybe they're not indicative of the code that you're running in production right now. Maybe it's too like math-oriented. They're good, and if you're writing code that is represented by those, you should definitely pay attention to them. But if you are using higher-level modern frameworks, you should take a look at the Renaissance benchmarks as well, right? And you can see that the performance varies. And there is an important fact is, so the GraalVM Community Edition, because this is very often the question, like, what is the deal with the Community Edition being slower than the Enterprise Edition? It's not slower than the Enterprise Edition. The Enterprise Edition is faster. There is subtle difference. It's faster because there was more work put into that, right? And you can see that the Community Edition is, sometimes it's faster than OpenJDK, which is yellow bars. Sometimes it's significantly faster. Sometimes it's on par. Sometimes it's a little bit slower. So the Community Edition is volatile, right? If you happen to have a workload that is really good on the GraalVM Community Edition, God bless you. You can run it, you can get the performance boost, right? But you need to understand better what you're doing with regards to performance. You maybe need to have performance tests or something. The Enterprise Edition is almost universally better than OpenJDK, right? So, which is a very significant difference. Right, so benchmarks. Oh, good point. We also in the community, in the ecosystem, we have OpenJDK, the project, right? And GraalVM and OpenJDK, they have a little bit different visions. OpenJDK is a very important project in the Java ecosystem, and well, it's not going anywhere, right? They power the deployments of like, literally millions of deployments. There are reference implementations for the JVM. GraalVM wants to be the high-performance polyglot virtual machine for all languages. It's a very different vision, and it's a different process to get there. So you need to be aware that both of them are friendly open-source projects. We are taking OpenJDK as the base platform for our JVM runtime, right? And they're taking compiler, Graal compiler, a version of that, of the open-source compiler, and put it into OpenJDK. So if you're running, I think, 10+, you can try a version of the Graal compiler without downloading anything. There is a version of the Graal compiler built into your OpenJDK distribution. You can turn on a couple of command line flags, you can run it, and it will run with the GraalVM compiler, right? You unlock the experimental VM options, you use JVM CI compiler, and you check on the results. As I said, it might be possible that for your particular workload, it might be on par or a little bit slower. It also is possible that it's much faster as well. So we took a look at this one benchmarks, and I'm going to speed up a little bit. It's a benchmark to multiply matrices, right? So of the complex numbers. And the trick there is that the implementation inside uses the immutable data structure for the complex number. So it's two numbers, right? And when you do any math operations, it creates a new object and puts the results of two numbers there, which is very good from the programmer point of view, because it means that you can reason about this code very easily. But at the same time, it generates a lot of objects. So it pressures garbage collection, and it might be slower than it could be. So when you run this on the JDK11, and it's just JDK11 with Graal compiler enabled by the command line options, the difference is almost 2x. This is also the results from this laptop, so take it with a grain of salt. But it is very representative of this workload. So Graal compiler has extremely good escape analysis, which means that it can eliminate object creation quite a bit better than C2, right? And if you have the workload that is producing a lot of objects, you would probably see the performance boost. Also, high-level patterns, stream API usages, and so on. Right. So Twitter is one company that is using Graal compiler, GraalVM compiler, from the GraalVM project. In production, they run their Scala microservices with it. Chris Tallinger, who is also here, I think he has a session tomorrow, talks about how they use that, shows some graphs. If you want to go there, close your eyes for a second. Spoiler alert. They show typically these numbers. So out of the box, they can reduce the CPU time, like make their programs faster around 12%. and then you can tune it a little bit more, and up to like 18%, which is a lot. And they can save money on the hardware. They can save money on the electricity. They can save a little bit of the environment, which is very important currently in this age and time. So they are doing a good thing by running their Scala microservices with the GraalVM compiler. Applaud Twitter. Twitter is good. Right, so you can do this as well, right? But you have to understand what you're doing. They have very brilliant engineers who understand how virtual machines and the compiler works. So they have the capacity to tweak it and use it, right? You might too, but it depends on the use case. Right, so it also usually, one of the best parts about Graal compiler is that the compiler written in Java. And for some time now, since we released the first release candidates last April, it was the case that to get to the peak performance, we needed to warm up the compiler quite a bit. Because it's written in Java, so it goes through the same compilation pipeline. So before your program gets compiled, you need to compile your benchmark harness. Before your benchmark harness gets compiled, you will probably compile the compiler itself, because it's the same Java code. So it took like longer warm-up times, and it wasn't the best. So recently, we converted the GraalVM compiler into the native executable shared library using the same GraalVM native images technology that you can use. And currently, it's enabled by default. So what you can do, you can turn it on, and the warm-up on the current versions of the GraalVM distributions will be very similar to the warm-up times of the C2 compiler. So if previously, say, an execution of a small Java program counting words was one number, so now it's much, much lower, right? So it might not matter in the long run. If you run your WebLogic servers for years without restarts, or for months, or weeks, even days, even like hours, maybe minutes. If the JIT compiler gets to optimizing your code, then it can amortize the startup cost, right? So it wouldn't matter. But it's better to have a faster starting JVM. And now we are much faster than at the same time last year. So enough about Java and the JVM. Let's talk about other things that the GraalVM can do. GraalVM can give you the Polyglot environment, so you can enrich your programs with packages in other ecosystems. And I'm going to show you a demo. And it's going to be a Spring application. Who uses Spring? Excellent. Who writes web applications but uses something else than Spring? Excellent. More Spring people here. Very good. I'll show you a Spring application. I would show you a Spring application regardless, because I have the Spring application demo here. But it's nice to know that it's a good fit for the audience. And what the Spring application will do, it will, oh my God, this is the IntelliJ IDEA that I killed before that I need to restart. Excellent. What this Spring application will do, it will be enhanced with some R for the data visualization, right? Different languages are great at different things, right? So R, for example, is great for data science or machine learning. Python is great for machine learning. Everyone in the world, almost everyone, doing machine learning, they're like, Python is our language of choice, right? So if you would like to do machine learning, maybe you would like to use the ecosystem of the Python libraries. And we can give you that on the JVM. While I'll talk, I will start this thing. So it's a Spring Boot application, and I will just run it here. And it will start in a second, because it needs to load, compile the things, and then load the R standard library. It will start, and then we'll look at the code when IntelliJ IDEA will start as well. OK, cool. So this is the code. I have a normal Spring application, right? It's a Spring Boot application. It declares a controller. It declares some beans. How it uses the GraalVM, it creates a context for the languages to evaluate programs in other languages. It has this magnificent file called plot_r, which is the R function written in R. This is R code. I'm not 100% sure what is happening there, but this is how people write R code. Well, amateurs. I wrote it. So how amateurs can write R code. So what we do is this. It declares a function, right? So this module, R package, will return a function. How we can use that in our Spring application? We declare a context to be able to evaluate languages. Then using that context, we say, I would like to declare a source, and I will say that it's our source, and I will pass this file to the source thing, and then I will evaluate that source inside the context, right? And I know that out of that file comes a function. So I want to say, I want this value, this interoperability value, as a function. So GraalVM offers the Polyglot API to make the interop between different languages as simple as possible. I like to think that it's a very reasonable API. So there is a class value to represent object in any language, and there are ways to convert that to classes and objects in other languages. Like using, for example, on a dynamic language site, it's very easy. Like you write it in JavaScript, you say like, oh, I get this value, and then you don't care about the type, right? It's dynamic type. You don't write it out. On the Java side, you need to convert that, and here we convert that to a function. And this function is a Java the normal function, right? The normal public interface. And after that, I can use that R function normally, right? So I assign it to this auto-wired bean, and don't do that. Don't use the field injection. But after that, I can just use that. I call the apply method on that. I pass the normal Java objects to that R function. And I uploaded some details. I get the string back out of the R function. I get Java string. This is a little bit mind-blowing if you think about it. And then I return that to the browser. So my function, my thing started here, and I will try to localhost it 8080 load, and we'll see what it works, whether it works or not. Let me. It will start a little bit. It will take a little bit of time on the first request, because it needs to load, it needs to initialize, and it starts running R in the interpreted mode, but then it compiles it faster, and it runs faster and faster. So you can see it just gets random data from my system, passes it to our plotting facilities, and plots the graph. So this is how you can befriend different languages in a single system. And while it might seem like maybe not the most wanted feature that you ever wanted from your runtime, we know of companies and projects who use this approach. We know of the companies, and I'm very hopeful that sometime soon they will go and talk publicly about that, so I can actually name them. They use JavaScript inside the JVM with our interop to pre-render React applications for the first render on screen, right? So they want to render server-side, and they use that and render through JavaScript through this technology. There are a company who is experimenting with doing actual data science in R and running on this. So it is possible. People are using that. And if you see a proper use case for that, maybe you want to use it too. Right. 30 minutes. Let's speed up a little bit more. JavaScript. Our JavaScript is excellent. It's very compatible with the modern standards, right? So JavaScript evolves regularly as a language. It moves forward really fast. We are currently compatible with ECMAScript 2019, which is I think it's a draft of a standard. It's not even the fully fledged standard yet, but it's a draft, and we're compatible with it. We are as compatible as Node and browsers, right? So it's a very solid level of compatibility with the standard. Why we can do that? Because we don't need to translate that to low-level, like bytecode or machine code. We just need to describe that in the interpreter. It's also reasonably fast. V8, the normal virtual machine for executing JavaScript, is a great virtual machine. So it's really hard to be faster than that. And we are currently, I think, a little bit slower. So if you want to run JavaScript for performance reasons, maybe this is not yet our chance. But we are the fastest JavaScript engine on the JVM. So we run Octane benchmark, normalize that to Nashorn results. And the community edition is approximately 4 times faster. Enterprise edition is approximately 6 times faster, which is many times faster than Nashorn. And I think we're something like 15% slower than normal Node with V8. On the plus side, you can run node applications with giant heaps because we can run it on the JVM, making sure that we leverage JVM's infrastructure, like normal, not normal, state-of-the-art garbage collection, like G1GC, or there's something that can handle giant heaps, right? And it will work. If you want to do that, probably GraalVM's JavaScript engine is your best bet. So JavaScript is fast. You can use our JavaScript implementation also on the stock OpenJDK with just a bunch of dependencies. The downside there is that in the presence of the GraalVM compiler, those languages will run faster because of the Truffle Framework has some dependencies on what it expects from the compiler, and GraalVM compiler offers those things. Would be kind of silly if it wouldn't, but with other compilers might not offer them yet, right? So with Graal compiler, that will run also fast, but without, it will run kind of sluggishly. But you can still run it. Our Ruby is very fast. Unfortunately, I think currently we don't run Rails applications out of the box. Rails is the big web application framework for Rubies. We run small Ruby applications, and we'll get to that compatibility. JavaScript compatibility is 99%, right? We run NPM modules, we run JavaScript modules, we download them, we run their tests, and we know that we, as a platform, behave in the way they expect us from us, right? So compatible. Ruby is a little bit less compatible, but it will get there. R is recently has made a lot of progress in the compatibility with the ecosystem, right? So we added compatibility with modules normally used for data science, like data table and DPLR, right? Those are the underlying blocks that the whole ecosystem uses because they're the basic blocks, building blocks. So our R is much better, in a much better shape than, say, last year, and it's also really, really fast compared to GNU R, right? Our Python is the youngest integration. We are making progress. We are trying to get the compatibility specifically for the first, in the first hat was the NumPy, SciPy modules to get those machine learning use cases handled to make sure that we can run them. It might take a little bit of time for Python, but we can run like Python scripts, Python code very well, right? It's the native extensions of the existing ecosystem modules is what presents us with a higher challenge, right? So, but Python works. I know that there are builds on the developers' machines where we can run certain NumPy programs, which for developer speak, it works on my machine. Right, so Python. And you can mix them, and you can use the same tooling, which is very interesting. As I mentioned, the tools can integrate with the platform, not with the languages themselves, right? So we can use the debugger based on the Chrome inspector to debug Ruby code, or debug Python code, or debug a mix of those, right? We have the heap viewer, so you can profile your heap and see what's happening there in all those languages. We have the profiler, the tracer, and the sampler, and they work with all those languages. Last year at Oracle Code 1, Goldman Sachs engineering people had a session about how they try to migrate an internal language. They have a language for credit and risk calculations, and they maintain that for like 25 years, and that's a lot of work, but they cannot like migrate because they've written so much code in that language that they cannot just rewrite that. So they have to maintain the language, but it's hard work. So they did a session about how they try to migrate that to the GraalVM stack, right? And they iteratively took that approach. They did some basic steps, and I think the happiest they were is that they got the integrations with the tools ready, right? So with a very simple and fairly short time investment, they got the tools working, and they were like, okay, we don't need to maintain our debugger infrastructure. Like, this is really good. So if you have an internal language that you maintain for 25 years, maybe we can take part of that burden on ourselves. Right, native images. We have 6 minutes, and we're going to cover that in 6 minutes. GraalVM native images. What it is an ahead-of-time compilation of Java bytecode to machine code, right? So a GraalVM compiler, is a compiler that normally would be used as a just-in-time compiler, What it means, it takes the bytecode, and it takes the profile of how this bytecode is executed. Which code paths are taken, how many times we hit one if statement or other, what are the types of the parameters, right? The code and the profile. What happens if we don't give it a profile? It can still do its work, right? It will somehow produce the machine code. It's just like, okay, the profile is null. Let's not crash, but let's do our best to optimize this machine code, this bytecode, right? So if we do ahead of time compilation, this is exactly how it works. We don't give it a profile, and we just give it bytecode. And it can compile that to machine code. So technically, on the method signature levels, very simple. Technically, not so simple, but it works. It also works with the primitives and components of the virtual machine. So the resulting program will work with the memory management. There is a GC running in there. So your program can execute under the assumption that the memory is infinite. You can embed that. You can build a shared library. And in general, this is the idea of the GraalVM native images. It's normally you have a JVM, and then you dynamically execute Java code on top of that, right? So when you do the compilation, everything gets precompiled. And there is just one blob of machine code, right? The binary file. How it happens? We take a look at your classes, at classes of your dependencies, the classes that you use from the JDK. So all those classes, we look at them. We find all code that is reachable, like all the methods that are called, all the fields that are ever touched, right? We look at that under the closed universe assumption. We think that, OK, this is what we do. We will not execute other code. And then we compile that ahead of time into a native binary. And then we add a wrapper for the operating system to make this executable, and it runs. There are some challenges in this approach as well. Like sometimes you can be very dynamic, and then the static analysis which runs when we generate that cannot figure out everything by itself, right? So for example, if you use reflection and dynamically load classes and everything, it might be hard for the static analysis to actually see what you're doing. It's impossible, actually, right? So you can provide a configuration file that will suggest that you will use certain reflection bits, certain classes through reflection, or you will generate proxies, or will use certain GNI libraries, right? So you can give hints to the native image utility to generate those, right? And then those things will work as well. And even better, you don't actually always have to generate that by hand, right? You can easily use the framework that figures things out for you, or you can use the tracing agent and execute your code on the JVM, and it will record some information, and you can have multiple runs, and it will record the information which features were executed that need this additional configuration, and it will generate that configuration for you, right? So you will run your application using normal Java with a Java agent, and then you will get the configuration files back, right? So, and then you can use them to generate the GraalVM native image. The benefits of this are clear. The startup time of those applications are on par with the startup time of native languages, something like Go or C++. The memory overhead is very much reduced from the normal execution as well. And it makes those kind of deployable artifacts much more interesting for the cloud deployments, right? There are a number of frameworks in the Java ecosystem which embraced the GraalVM native images as the target. One of them is Quarkus by Red Hat. There is also Micronaut, which supports GraalVM native images as the platform. I know that there is a framework called Helidon by Oracle folks. They also support GraalVM native images as a platform. There are also certain kinds of Spring applications, namely mostly coming from the Spring Foo project, which can be compiled to the native applications. There are still some issues that we need to figure out with the normal Spring applications, but we are making a lot of progress for that. Right. So native images, we're working on Windows and Java 11 bits to make it work in those contexts. I know it will happen very soon. We have an experimental version of the Oracle database where you can try and execute stored procedures written in JavaScript. We can run LLVM bitcode in a managed mode. So that means that all the random pointer accesses to random memory will actually not be segfaults, but will be normal Java exceptions. So it will not allow hackers to kind of overwrite memory and exploit your vulnerabilities, but you will get an exception. And you can debug that. And we can do also other important and interesting things. So what you want to do with GraalVM, maybe you want to read that blog post about 10 things. You can see how it can help. And you want to remember that it's high-performance, language-level, polyglot virtual machine, embeddable across the stack in native JVM-based applications. And you can get those things as values from GraalVM. Right. So we're out of time. So please, the source code is there. Test your applications with GraalVM. Now we have a product announced as Oracle. Maybe talk to your manager about that. Just kidding. I mean, if you want to talk, but that's not necessary. Join a conversation. The more code we run on GraalVM, the more we are sure that it is very mature platform, and the more people will be excited about running their code on GraalVM. So join the conversation. Thank you. So I will pack my things very slowly, so you can have a chance to ask them, and then I will be at the booth or in the intranets. Thank you.